So cool. So if you're one of those that likes to look ahead, this part, actually there's no homework at the end. There's no homework anywhere in it. Yay! Part 6, there is no homework. So I just want to get through part 5. I don't think part 6, maybe there is homework in part 6. But anyway, I want to get through part 5, and then part 6 is physical phase diagrams, and it's kind of short. So what I'm proposing is basically do this today, and then call it a day. We'll probably get done a little early, I think. And then on Friday, we're going to do part 6, and then go back and pick up what we need to with the Clausius Clapeyron, the heat of vaporization on Friday. So there will be homework that I sign on Friday, due Monday. Okay?
5 and 6 don't, but 7 does.
Oh, 7 does? Okay. What is 6? Oh,
I don't think 6 do.
yeah.
Yeah,
Maybe that's more descriptive. Okay.
Yeah,
7 is
seven's
phase
short,
diagrams.
but
Oh, yeah.
7.
Thank you. Okay, so I'll have to think about that. But I still think we'll just do this one today. This part and the next part is like descriptive chemistry, where it's not really, there aren't any numbers. So, yeah. And actually, sometimes I do this part before I do some of my other parts, but this time I just kept it in order. Because some of the stuff would have been helpful earlier. You'll see what I mean. So there are different ways to like describe a compound or describe the situation with a molecule. You guys have done Lewis structures, right? And actually, you guys have been seeing some, I have examples of these. The Kukulé structure, the structural formula, just different ways to kind of show how the molecule is arranged. A semi-structural formula and condensed structural formula are kind of similar. And like I said, it's going to be easier to show you, and you've been seeing some of these. The line formula is kind of where, well, I'll show it to you. The line formula only has lines. Yeah. Yeah. And then these should seem familiar. The molecular formula of a compound and the empirical formula. The molecular formula, I say, is the real deal, how many atoms of each type of element there are in that repeating molecule. We can, if we can divide by a whole number and get another set of whole numbers, we can reduce it to an empirical formula. So an empirical formula tells you what elements there are in the relative amounts, but not in the exact amounts. So you can scale up an empirical formula to get a molecular formula. So this can be reduced. Maybe. All right. Okay, so here we go. Here's some examples. So this is the Kukulé structure, okay? This is, I believe, the description was there are no lone pair electrons being shown necessarily. So that's how it differs from a Lewis structure. Of course, there are no lone pairs to show here. What's that?
Well, that's not a good example.
I know. Well, just bear with me. So these are all the same thing. These are all C4H10. It's what we call a saturated hydrocarbon. It's an alkane. But these are showing you the same thing. This is where basically you have to be able to unpack those two methyl, we call those a methyl groups, kind of to interpret that as this. These are the same thing. Okay. This is the same thing. There are 4 carbons here. Now I think we've looked at benzene. This is similar to, remember the whole benzene ring? Okay. Where every time you see a vertex you think carbon. Okay. That's the same thing here. Every time you see down here vertex, think carbon. Carbon, and actually there's a carbon on each end. So that is still your C4H10.
Okay, and so and then the H's are also implied.
Yep, they're implied, exactly. And
they're. How many H's there are?
How do you know how? That's a good point. Do you remember the expected valence of carbon is 4? So it reaches out 4 times in a Lewis structure. So it'll reach out 4 times here. So since these are just single bonds, these are all just single bonds, no double bonds there, then that means, for instance, this carbon is reaching out 1, 2, and then you add hydrogen to make up the difference. So since it's reaching out twice, yep, it's implied 2 more hydrogens, like that. Yep. And then this one is 2 hydrogens. And then this one since it's only reaching out once here, it needs to reach out 3 more times. Yep. And this one 3 times. Bless you. So that's how you kind of unpack that line structure. Yep. If there had been, and it's possible there could be, actually carbon-carbon, and let's go ahead and make a double bond here, carbon, single bond, okay? In this case, actually, see this guy has 3 hydrogens. This guy right here, though, how many hydrogens does he have? Just 1, yep, 1 hydrogen. And how about this guy? 1 hydrogen. And by the way, you wouldn't see that carbon there, I just drew it there. And then how many hydrogens does this guy have? 3. Yep. So actually this, as a line structure, would look like this. Okay, where there's a carbon at the front, a carbon at the angle, a carbon at the angle, and a carbon at the tail, if you want to look at it that way. Okay, cool. So these are all, again, C4H10. Okay. So we talked about branching before. Okay, just look a little bit of branching here. By the way, when you go to name these things in organic chemistry, we'll talk about how you name organic compounds, but you look for the longest hot dog, you look for the longest chain, and to me, you know, it's kind of set up to look like that. You might say, well, what if I would, instead of going that way, what if I would go like this, and you'd still get the same number of carbons, and then you count them. I'm getting 1, 2, 3, 4, 5, 6. I'm getting 6 carbons right there. Okay, so actually that 6 is going to be kind of your base. So actually it's going to be a type of hexane. And you're going to describe the branchings. To describe the branchings, I don't know if you necessarily want to know this, but you always describe the branchings with the lowest numbers possible. So if it's going to be a type of hexane, that's the last name, okay, we need to describe these branching, this branch, these 3 branches. Basically, they're all cute little methyl groups. So in this case, to get the lowest branching possible, we can call this carbon 1. You have to enable, this has been a long time, but you have to number your carbons. We'll call that carbon 1, carbon 2, oops, you know what I mean, carbon 2, 3, 4, 5, okay, and 6. And I did it that way starting with from that end because then I can actually have lower numbers here. So to tell you what the methyl groups are, it would be, gosh, this has been too long, I might butcher this. But it would be 2, 2, and then you have to pick up this one, 5, trimethylhexane. This grows right there. I ran out of room.
So the 225 is part of the name.
It's part of the name. Yep.
It's where they're attached.
Yep. Yep. But I can see this one pretty good without my scribblings. This one is actually the same one with the same types of branching. To me, I have to concentrate, okay? Because this is actually showing you a carbon is part of the bone, okay, that has a 3 methyls. So methyl that kind of completes the main backbone, and then 2 methyls, this would be like our second carbon coming off. And then this one down here, this similar, 1 carbon kind of going out this way is the way I think of it to kind of make our 6 carbons going across, and then 1 carbon branching off.
Why wouldn't,
So like,
why wouldn't that be switched? Why wouldn't the first carbon hydrogen be on the, and
this
then
one,
the,
or over this one over here?
yeah, why wouldn't that be, and then closer to the middle? Because it's on 5 and not 6? Because that, there, to me, I would think it was on 6, not on 5.
Yeah. The way this is this carbon corresponds to, make sure I get this right. This carbon corresponds to this carbon. So then one of these carbons actually is this one to finish up,
Oh, I see.
and the other carbon is kind of branching off.
Got it.
Yep. Yeah, it's neat. So you're actually kind of seeing why, You know, you could write this, my gosh, I don't know what the formula would be, but you could, let's see, what did we say, 6, 7, 8, 9. You could write it as C9, and if it's saturated, C9, and some of you guys maybe already know what saturated means, but if it's just a hydrocarbon with hydrogen and carbon, you know how many hydrogens if you just take 2 times this, 2N plus 2, basically. So 2 times 9 is 18, plus 2 is 20. Okay, so we could prove it to ourselves, but there should be 20 cute little hydrogens, okay, scattered about. But the formula C9H20 is a heck of a lot, like, non-descriptive than this sort of thing. Because we know that, you know, it makes branching makes a difference, you know. So we can have different, what we call isomers of the same compound. All right. So there's the Kukulay structure. And actually, we are going to call this a carboxylic acid coming up. You know it's a carboxylic acid if you have, on one carbon, you have both a double bond oxygen and an OH. Okay, carboxylic acid. But does this look like you're missing lone pair electrons? Yeah. Because look at that oxygen. Look at both those oxygens. They don't have a complete octet. But we knew if we drew the Lewis structure, I guarantee you, you'd come up with something like that. Okay. But this is not a Lewis structure. Whoops. Okay, so that's a Kukulay structure. Well, it's saying Kukulay. Okay. And here's the same carboxylic acid with the structural formula. It's a little less descriptive. You have to, in your own imagination, take those hydrogens and fling them off the carbon. And here's the line formula, okay? So if it's not a carbon, carbon and hydrogens are kind of implied in the line formula. Anything other than that, you have to go ahead and write it. It kind of makes sense, okay? So here are carbon, 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 carbon. Right, and then of course we had 3 hydrogens, 2 hydrogens, 1 hydrogen, and 2 hydrogens?
None.
No.
None because of the.
No hydrogens in the last one?
There's only 3 carbons. 'Cause
Oh,
the
yeah,
N
thank
is
you,
the
yep.
OH.
Gotcha. You're very good. Yep. Because if you were going to do what we did before with this carbon, you'd say it's got, yes. It's got 1, 2, 3, 4. It's all we're reaching at 4 times. No places for hydrogens. Oh, but what about, oh yeah, it had a vertex, but it's not a carbon there. Sorry. Okay. I gotcha. I gotcha. Okay. Oops. So here they are all together, the same structure. All right. So this is actually kind of something I've already said before. If you have a formula and somebody has to give you, for you to say the polarity of that compound, and it's only got carbon and hydrogen in it, you can pretty much say it's nonpolar. You can pretty much say it's nonpolar. Whether it's what we say saturated or not, it is nonpolar. Okay? So if something has only hydrogen and carbon in it, it's called a hydrocarbon. It's kind of nice when names fit what it is. And actually there are different versions of hydrocarbons. We were looking just a little bit ago at what I call saturated. And you can kind of think it's saturated with hydrogen. Alkanes are saturated with hydrogen. Alkenes have, I'll go ahead and tell you, alkenes have a double bonds. That's my little double bond. Alkynes have triple bonds. And we're going to see with double bonds and triple bonds kind of embedded in there with their carbons, then the carbons actually aren't what we say saturated with hydrogen.
What do you say the last one?
Alkynes, triple bond. Benzene, we know what that is. That's that circular sort of 6-sided thing, C6H6. And alkyl benzenes, we've actually already seen them before. A benzene ring is very reactive, and you can substitute things on, like kick off hydrogen, put something else on there. If you put like a methyl group, What's that?
Like glucose?
Yeah, like glucose. It's getting a little bigger than we'll probably be getting to, but yeah. Glucose, though, has oxygen, so it would not be a hydrocarbon. Yeah. But right idea. Okay. So hydrocarbons are nonpolar, which sometimes you need to know that. So here are some alkanes. The simplest alkane is methane with 1 carbon, 4 hydrogens. Then we use this actually between 1 carbon and 4 carbons. Of course, you could have something that's 2 carbons, 3 carbons, and this is 4 carbons. We use the prefix BUT for 4. Okay. And here is a something kind of we looked at. Let's see if we can kind of apply what we did before. The main, the longest strand you can get is 6. There are 6 carbons, 1, 2, 3, 4, 5, 6. Okay. And we're going to go ahead and have to name our methyl groups. And the best we can come up with is start with number that carbon 1, 2, 3, etc. So that's why it's 2,3-dimethylhexane. So, yeah, this sheet I gave you, actually a few things. Notice it has not my current name, but this is my maiden name, so this is very old. This is, I was looking for something to give to students one time, and I was like, well, I know I've seen that in my old organic textbook. So this is from the inside cover of my old organic textbook. But the way you read this is, like if you go to the formula, you see those R's. Those R's could be anything, okay? Those R's just mean something, okay? And the crux of it is, though, like for instance, if I said alkynes were triple bonds, so if you go down to alkyne, you see R, C, triple bond, C, R. So R is anything, and what's most important with alkyne is the carbon, triple bond carbon. Okay, so that's kind of how they work.
What's X? Is that?
X is a halogen, so like a group 7, 8
Okay, I
element.
didn't know if it was used as a element or if it's.
Yeah, it's used as a specific type of element. So,
Okay.
yep.
Awesome.
You said halogens?
Yeah, halogens, like down here, it's called a halide. So, yep. Yeah, so I thought this is kind of helpful. Some of these we will be talking about. Remember I said a carboxylic acid? Let's see. Yeah, it is alphabetical. Find carboxylic acid, and it's like I said, if you find a carbon, double bond oxygen, and that same carbon is bonded to an OH, that is a carboxylic acid. Now, it's possible, as I was looking at this, I'm like, it's possible to get kind of a mismatch of something that basically an awesome biomolecule that has kind of an assortment of these, but you kind of isolate it, and you could refer to kind of parts of it as pertaining to this. All right. Cool. All right. So alkenes, I said double bonds. So you can find alkene here. So it's a carbon, double bond carbon with R's. Actually, I'm kind of liking this third column here. Like, for instance, it goes ahead and it tells you alkenes. Here you have carbon, double bond carbon, but in order for those carbons to finish their set of 4 reaching out, they're actually going to have to be bonded. Each carbon's bonded to 2 other things. Now, that could be another long set of carbons, or it could just be a hydrogen. So propene, pro is P-R-O-P, prop is 3. So propene is a 3-carbon molecule that has a double bond in it. Now the problem when you get more than 3, more than 3, is that double bond can go different places. So actually in the name, and like I said, it's been so long, but somewhere in the name you need to say where the double bond is. So here we have PENT, pent is 5. Okay, so again, kind of like we did with the alkanes, you can get 5 is your longest, whether you go that way or whether you go up, you still get 5. And notice that it'll be called pentene, and to say where the double bond is, we say it's on the second carbon. So 1, 2, 3, etc. Notice that there is 1 methyl group also on the second carbon. So it's 2-methyl, 2-pentene. Okay, so the longest we can get here is 4. So 1, 2, 3, 4. Okay, so this is bute. We use BUT for 4. So this is butene. Now that double bond could have gone here, here, or here. So again, we have to say where the double bond is. It's very symmetrical. If we go ahead and call this carbon 1, carbon 2, oops, carbon 3, etc. Okay, so we're going to say it's the second carbon 2 butene. Now, we're going to actually talk more about this word trans. This word trans actually kind of puts one more spin on it. Does it look like, and if you kind of like a cheerleader, like does it look like this, like trans? Does it look like it kind of goes with regard to not the hydrogens, but the skeleton part of the molecule? It kind of goes opposite sides. Here's the deal, and I was talking about this to Marie the other day. If you ever have a double bond, basically there's no rotation around that. It's stuck. It is totally stuck. Okay? So picture these carbons as being there's no free rotation. Single bonds, oh yeah, it can rotate till the cows come home. Double bond, triple bond, it's stuck. So with that in mind, actually we end up with, we talked about trigonal planar structure. If you look at each one of these carbons, it's sp2 orbital hybridized. It has sigma bonds, 1, 2, 3, no lone pair electrons. It's trigonal planar. So basically that is a planar, this main part is planar. Now these aren't planar. These guys, these hydrogens stay out. Okay? But kind of these 4 carbons lie in a plane, as it turns out. So with that in mind, they lie in a plane like this. It's trans. Okay, it goes, it kind of jags. The other one is called cis, and it's like this. So a cis would basically be, again, it's a fixed position. Basically, swap one of these methyls and a hydrogen, switch it around, and it's like this. So there's cis and trans, and we are going to talk about that in this unit of material because we're going to see that they melt, like it has an effect on intermolecular bonds. But they're just what we call different configurations. All right, benzene, gotta love it. Okay, we've been talking about benzene. Alternating single, double, single, double, single, double bond. I know that's too many. And here's a substitute. Here's a substitution has happened here. This would be like an alkyl benzene. That's what I'm thinking of. Okay, its specific name is toluene. So they're at. You guys are good with this. There, that basically this hydrogen was kicked off and substituted in methyl group. Naphthalene, which is kind of a weird little child. Okay, again, it's just a hydrocarbon, so we have a carbon, 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 carbon. Okay, so the red things are carbons. And then kind of like benzene, these are hydrogens. So what do you think? Are there any hydrogens here? I don't think so. I think it's like, I'm kind of thinking this might be a double bond here. And then it would be done. We have to look up the formula for naphthalene. It's on your homework. What did it say? Yeah, thank you. So, yeah, it's kind of showing no other hydrogens. Yeah.
Bonds. Right?
Probably, I'd have to look. I think
I
probably.
copied how you did it.
Okay. Well, that may have been your mistake. But, because this right here, I'm looking, well, 4. This guy right here has 5 bonds. It's reaching out 5 times, so I'm just not quite sure about that.
Okay. I might have missed it.
It's C10
Yeah, yeah.
I must have misread it. I misread it.
Naphthalene. Okay, so believe it or not, those were all hydrocarbons. So hydrocarbons take some variations, right? Because they have alkenes, alkynes, and branching and all that. Now, we're stepping it up and we're adding oxygen. In general, like the slide says, if you add oxygen to your molecule, kind of think of it as being partially negative. It's going to bring a degree of polarity. It's possible that you have like this long, totally long hydrocarbon portion, and if you just have this one little double bond oxygen or whatever, it's not going to, it's a degree of polarity, but basically this nonpolar part takes over. So it's always kind of a mixed bag. It can be a mixed bag, okay? But there are some options here. Is the oxygen bonded to a hydrogen? If so, we said that that's a condition where you can have hydrogen bonding. And remember in our list of what's strongest, we said ion, ion, ion dipole, and then hydrogen bonding, and then ordinary dipole. Okay, so hydrogen bonding is pretty darn strong. But if your oxygen's just kind of stuck in there, basically kind of embedded, is kind of how I think of it, in kind of your sea of carbon and hydrogen, okay, if there's not a hydrogen stuck to your oxygen, then it can be polar, but it won't be able to hydrogen bond with itself. All right, so things that can hydrogen bond. So these must have an OH. By the way, OH, you'll hear people call it a hydroxyl group. OH is hydroxyl. So alcohols, phenols, carboxylic acids. These have an oxygen in them, but the oxygen is, like I said, kind of embedded between carbons. So it's the oxygen is not connected to a hydrogen. So these would generally be polar, okay, unless they get too much carbon chain, but they're generally polar, but they don't hydrogen bond. All right. So we use the term MET, or the prefix MET, like you saw methane a little bit ago. MET is for one carbon. ETH is for two carbons. So we have ethanol. Sometimes we call this ethanol, ethyl alcohol. It's like the same thing. So I have two carbons with a hydroxyl group on it. Notice that we don't care to say where the OH group is, because honestly, it could be at either one, and it'd be the same. But if you get up to three carbons, you do have to say where the hydroxyl group is. Now this actually, you see kind of the carbon, you see two hydroxyl groups. This is an example of, you can use the prefix di, as in di for this. This is a diol, an example of a diol, ethylene glycol. You recognize the benzene ring here? And a hydrogen's been substituted. You throw in a hydroxide, you throw in hydroxide. You throw in an OH group, and it makes it polar. So basically, you've taken your benzene ring and made it polar. It's phenol. This is the most basic carboxylic acid you can have. We know it's a carboxylic acid because you have carbon, double bond oxygen, single bond OH. So you have hydroxyl group, and you have, it's got a little bit of a power to it. This thing's running around partially negative. Okay, this is partially negative, partially positive. So acetic acid. We do in Chem 1, General Chemistry 2, we do a lot with acetic acid later on. So acetic acid looks like this. Propionaldehyde. Okay. Prop meaning three carbons. I guess I would say, aldehydes and ketones. So aldehydes, if you look on the sheet I gave you, to me, I always have to concentrate what's the difference between an aldehyde and a ketone. And if you look, you can see that if you compare an aldehyde with a ketone, the thing with an aldehyde is basically where the double bond oxygen is, that carbon has a hydrogen. A ketone, actually, there's something else over here other than a hydrogen. That's the difference between an aldehyde and a ketone. So actually, we kind of have some fancy names. These aren't kind of following our label which carbon your double bond oxygen is on, which probably you would need to do if you get kind of fancy. But these are very similar structures. They would have what? The same molecular weight, right? This first one is an aldehyde. Well, this has the name aldehyde in it. This one is a ketone. We know it's a ketone because there are, the carbon that has a double bond oxygen has two things that aren't hydrogen to them. So now this one looks similar, but notice it has looks kind of like our carboxylic acid, but the oxygen is embedded, not connected to a hydrogen. So this one would not hydrogen bond, but we do have, I'm believing, partially negative regions both here. So this is an example of a, is it acetate? There's a word coming up for it. An ester. Okay. This is, if you see, you can find ester down there, that's what this is. An ester is this. And this is an ether. I get my E's mixed up. So an ester is this one in the bottom left. And this is an ether. Okay. And we're not going to get into naming, but you can almost see why this is maybe diethyl ether. I don't know if I really. Eth is 2 carbons. Okay, so basically we have two carbons. So it's diethyl ether. Okay. So an ester, an ether. Switching gears. Now we have hydrocarbons with nitrogen. Hydrocarbons with nitrogen. I guess more specifically, I'm focusing on the nitrogen part. Now, generally, nitrogen-containing compounds oftentimes are called a type of amine. They have this fishy smell. We have primary amines, and the way you say a primary amine is do a kind of like a 1 with a little circle. That's primary. Guess how you do a secondary amine? A 2 with a little circle up there. That's secondary amine. Primary amine and secondary amine.
Sorry, what's the one of those?
They tell you, and I'll tell you what this is a primary amine and this is a secondary amine. It's a primary because it only has, notice the nitrogen. If you find the nitrogen, you can see if it's a primary, secondary, or tertiary amine. If it's only connected to one thing, carbon-wise, it's a primary amine. In this case, this nitrogen is connected to 2 carbon things. Because remember how that works? Basically, we could take this structure and expand it. We have a nitrogen, hydrogen, and then we have, okay? So this is actually an example of a secondary amine. This one over here, we have the nitrogen, hydrogen, hydrogen, and methyl group. So that is a primary amine. Guess what a tertiary amine is? Basically, we take this hydrogen and it's replaced with some sort of carbon stuff. That's a tertiary amine. Because you figure nitrogen wants to reach out 3 times. It's a group 5A, so 8 minus 5 is 3. So generally, when you're drawing your Lewis structures, it's going to form 3 bonds, single, double, triple, however that goes. If they're all single bonds, then it can bond to 3 things. Okay. So in this case, this is a tertiary amine because the nitrogen is actually on all of its singly bonded to 3 carbon things. So it's a tertiary amine. 3 carbon things. Now, hydrogen bonding is a big hairy deal. So that's when oxygen is bonded to, when hydrogen is bonded either to an oxygen, I'm looking at the periodic table, oxygen, fluorine, or nitrogen. That will give you your hydrogen bonding. So, hey, we have hydrogen bonding, right? And I already erased it. But we had hydrogen we had hydrogen bonding right there, where we have nitrogen, hydrogen, hydrogen, and carbon. Okay, these are our hydrogen bonding sites, where this is partially negative, kind of like the oxygen was, and these are both partially positive. And we have hydrogen bonding here, right there. Notice that, like the slide says, you can have no hydrogen bonding there. But on a slide coming up, I'm going to show you how you don't have hydrogen bonding, but by golly, this nitrogen right here runs around partially negative. So if you, it can hydrogen bond, but not with itself, because it doesn't have a hydrogen in its pure state, a free hydrogen that's bonded to another nitrogen or oxygen or fluorine. So it's possible to hydrogen bond in a mixture. So I feel like this is kind of review stuff, so don't go to sleep. Let's see. So if you, hydroxyl, that was the name I was trying to find, not a minute ago. So if you have a hydroxyl group, an OH group, which makes it an alcohol if you just have one hydroxyl group. But actually alcohols then they are polar, and so they have stronger intermolecular bonds, so they're going to boil at a higher temperature compared to similar weight alkanes. Let's see. So you're like, ether, well, what's that? Well, you can just grab this little sheet, find your ether. You're like, well, what's an ether? And I do like this column right here. What's an ether? So it says dash oxygen dash. So basically you have an oxygen that's kind of embedded in your carbon chain. So it doesn't hydrogen bond, but it's partially negative, makes it polar, but it's not as strong as an alcohol. Boiling point increases as you increase carbons in your alcohol, and that makes sense because you get more induced dipole. If you have branching, okay, remember that's kind of balling it up, and it's less likely to be able to induce a dipole. So branching, actually the same molecular weight, makes it, will boil at a lower temperature. Same number of carbons. Boiling point will increase with increasing number of hydroxyl groups. So a little bit ago we saw a diol. You can have multiple hydroxyl groups, and the boiling point will increase as a reflection of increased intermolecular bonds. Okay, so last Monday when we were in here, we talked about solubility, like dissolves like. Okay, so if you're talking about alcohols again, and as long as if this is your hydroxyl group, as long as you don't get too many carbons, and actually the limit here is 3. If you get more than 3 carbons, basically you're taking on a non-polar characteristic. Otherwise, 3 carbons or less, it will dissolve infinitely in water. Because water is polar, so it's looking for something that's polar. If you have 4 alcohols or more, it's only soluble to a certain degree. Of your of your butanols, basically, if it's all balled up in what we call tert butanol, then it's more likely to be soluble in water because it kind of minimizes the alkane portion, I think. All the 4 alcohols. All right. Like I said, as you add on kind of the carbon chain to your alcohol, it becomes insoluble or less soluble. So I was looking at this at my office. In order to kind of talk about alcohols, what you need to do is just focus on the reds. Okay, so the reds are basically looking at alcohols. The blacks are looking at something else. So over here, you can kind of see the corresponding reds. This is increasing numbers of carbons. All right, so there's methanol, the simplest alcohol. I think this is kind of weird, and this actually is what Marie was talking about, that there are biomolecules out there that basically take advantage of having a polar and a nonpolar characteristic in the same molecule. Yep. So just little simple molecules of like an alcohol. The green portion would be nonpolar, because the green portion represents your carbons and your hydrogens. Okay. The last, I think this is kind of weird how they did this. Okay, so this represents your oxygen and your hydrogen. And this is your carbon, hydrogen, hydrogen, hydrogen. Okay, so these are all carbons and hydrogens. And this is your oxygen and hydrogen. So all it's saying is this is partially, partially negative, partially positive. And this is basically nonpolar. So this is the polar end, okay? The polar end, we say, loves water. So it's hydrophilic. It loves water. The nonpolar end does not like water, because water's polar. We call that the hydrophobic end. All right. This is methanol in water, and I kind of made it so we didn't see anything. Do you guys recognize the water molecules here? Okay, so the red here are oxygen and the blue are hydrogen. So that's water molecules, water with their hydrogen bonds. Well, methanol can hydrogen bond too. Okay, methanol is the simplest alcohol there is. So with methanol, what you see here is the black, the carbon. This is your methyl group, carbon, hydrogen, hydrogen, hydrogen. This is your hydroxyl group, and notice it is hydrogen bonding with the water molecules. Okay, so this is what like a mixture of water and methanol would look like. And it's infinitely soluble. Polyhydroxy alcohols. Okay. The more hydroxyl groups you have, the more soluble it is in water. Makes sense? All right, back to carboxylic acids. Okay, so carboxylic acids, we have basically two regions, that's the way I think of it, of electronegativity differences, kind of here and here. So carboxylic acids definitely can hydrogen bond, plus they got the kicker, the partially negative oxygen that's doubly bonded to the carbon. And these, like it says, will have stronger bonds than, remember we talked about just regular alcohols, because they just have that. Ketones or aldehydes just have this, and they have both. Makes sense? We'll talk more about how the temperature at which a solid melts is also an indication, to a lesser extent, of the intermolecular bonds. Okay, but this just says that the melting point temperature of solid carboxylic acids is relatively high. Would carboxylic acids be soluble? Yep, unless you get too many carbons. Because they will hydrogen bond with themselves and hydrogen bond with the water you're dissolving in. The limit is about 4. If you get 4 carbons on your carboxylic acid, it starts to be less soluble. Up to 10, it's insoluble. Very soluble in alcohol, makes sense. Most longer chain acids, carboxylic acids, are quite soluble in nonpolar solvents. Does this make sense? If you add a bunch of carbons onto your carboxylic acid, then basically you have made it nonpolar. Then your best bet to get it to solubilize is to grab something that's nonpolar. This is a ketone. An aldehyde would be where it's got a hydrogen stuck down over there. Okay, so aldehydes are ketones. So again, like I reminded myself, that would be an aldehyde. But both of them actually have are polar. So you might say, can it hydrogen bond? Well, and I don't know if you've caught this subtle difference, but honestly, it can't hydrogen bond with itself. but it can hydrogen bond with something that, like water, that can buddy up to it. And let's see, how would this do? Here's my water molecule. Here are my hydrogens. And you guys would tell me partially negative, partially positive, partially positive. So if you can actually get an intermolecular bond going between one of the partially positive hydrogens of water and the partially negative oxygen of a ketone or aldehyde, that ... that is a hydrogen bond. Okay. But it can't do it with itself. So finishing up with this idea. So I'm going to revisit amines. This is by that's a tertiary amine. Does it look like a tertiary amine? It's got three things, kind of three carbon things. Okay. Let's see. How did I do this? These right here, from left to right, this one is actually a primary amine, secondary amine, tertiary amine. And I think I mentioned this before. This primary amine, and you might run into this in some of your homework problems. The primary amine, do you buy this? That actually it's got two places for partially positive hydrogens to hydrogen bond. Okay? And so actually you would think that that would be stronger than the secondary amine because it only has one. Okay? And I'm going to kind of prove to you, well, not really, I got it off the internet, but this nitrogen here, actually it has a lone pair of electrons is partially negative. Okay, so this thing actually can hydrogen bond with, for instance, water or something like that. Tertiary amines cannot hydrogen bond to themselves, but, come on, this is what I got from the internet. They can actually, up here, this is a tertiary amine. It's a different tertiary amine, but notice you have a nitrogen and three methyl groups, right? So it's partially negative, and it can, that blue ... is a hydrogen bond to the partially positive hydrogen of a water molecule. It's neat, the things that you can get off of, I think it's Chem Wikipedia. Okay. So if you're ever faced with trying to wrestle with what's going to have stronger intermolecular bonds, and you have these kind of an assortment of amines, look to see if it's a primary amine, secondary amine, or tertiary amine. Okay. Cool. Well, that's all I got.